photodiode. Okay, that is we are discussing. Okay. Avalanche photodiode. Okay, so we have PN photodiode and PIN photodiode, and now this avalanche also PIN type only. But here the advantage of this avalanche photodiode is, suppose light intensity is very less. Okay, light intensity are very dim light. Okay, or you can say very light intensity is very low. Okay, low light intensity or dim light. In that case, we are the intensity is very less, so with that light we can produce only less number of electron and holes. Okay, if less number of electron hole means we can produce only less current only, so that means our response also very less. So in that case, even light intensity is low, we are creating some electron holes. Okay, we are creating some electron holes using multiplication process or impact ionization. Okay, here mainly what we are doing, impact ionization. This is a main concept we are utilizing in this photodiode. Okay, using impact ionization we are generating more number of electron and holes, and also here we are applying high reverse bias voltage. Two things we are doing. First one, we are taking p and highly doped, and we are using high reverse bias voltage. With this reverse bias voltage we are generating more number of electron and holes. Okay, that is the concept we are utilizing, and we are creating more number of electrons, and if electrons are more means we are getting more photo current, or more current we are generating using this photodiode. Okay, if photo current is more, that means responsivity or quantum efficiency is higher. Okay, that is the thing we are doing in avalanche process. Okay, so avalanche diode, we will take 3-4 layers. Okay, so here you can take uh, n plus region here. Okay, just I am taking a one vertical diagram, two diagrams I will explain. Okay, these are just I am drawing vertical diagram. Okay, this is n plus region and this is p region. Okay, n plus p. After that, I layer, I region. I region means intrinsic. There is no doping. Last one, P plus region. Okay, here first one, N plus and P plus is highly doped. Okay, highly doped regions. And here P region is there, that is moderate doped. Okay, so highly doped means we will have more number of electrons here, N plus region, and more number of holes available in P plus region. Okay, so here if you draw electric field profile for this diagram, okay, these layers, this structure, okay, this is the simple depletion width. Okay, this is electric field. Okay, we are taking along x-axis, suppose electric field. So in this region, whatever we are drawing in this region, at this depletion region, okay, this phase charge region, this is also just like Pn plus region, or Pn plus junction, or N plus P junction. This is also some Pn junction only. Okay, so here in this junction we are having high electric field. Okay, high electric field. Why we are having higher electric field means, because we are highly doping. Okay, this is highly doping. If doping is increasing means the electric field also increases. So del dot E is equal to, okay, del dot E is equal to, Gauss law, right? Del dot E is equal to rho by epsilon, rho by epsilon or epsilon naught. Okay, depends on medium. Okay, rho is equal to here charge density, electron charge and donor atoms. This is gives the charge density. Charge density rho is equal to E into ND. ND means donor atoms in layer are semiconductor. So from this expression, if you integrate this equation, you will get E is equal to, rho is equal to E ND by epsilon or epsilon naught, whatever you can take. So here you will get the space charge region. Okay, depletion width X. X is here depletion width. So here if you see, E is electric field is proportional to the donor density, right? Here concept you take here. Okay, the electric field is always proportional to the donor density. Okay, or you can say electric field is similarly acceptor density. this you can derive also. For in case of here you have taken donor atoms, or if you take holes, for in case of holes you can take rho is equal to ENA. Okay. So electric field is always proportional to the donor atoms. So how donor atoms are increasing? By increasing the doping. If we increase the doping, more number of impurities are adding, either acceptor atoms or donor atoms. Okay. So here n plus region, n plus means donor. So we are adding donor atoms. In n type semiconductor, we will add impurities. That impurities we are calling donors because they are ready to donate electron. So in case of p type semiconductor, we will add impurities. These impurity atoms we are calling acceptor atoms. So this semiconductor, p-type semiconductor, ready to accept electron or ready to donate holes. So we are talking about with respect to electrons. That's why p-type semiconductor always ready to accept a electron. That's why we always call it a acceptors. Okay. So here high doping is there. So n plus region highly doped. So that's why here doping is increasing means number of donor atoms are increasing. Okay. ND is increasing here. Okay. ND is increasing. If ND is increasing, the electric field also increase. That is the relationship between donor atoms and acceptor atoms to electric field. Okay. So after that, here in the I layer, the electric field is constant. There is no dopant atoms, there is no acceptor atoms. So compared to n plus region, doping is higher than the p plus region. Okay, that's why here we are drawing a little electric field. Okay, this kind of structure is there. Okay, only this first region, whatever we have taken n plus p region, this highly doped. So that's why here electric field is high. This region we are calling a avalanche region. What is that? Avalanche region. Okay, avalanche region. This space charge region here n plus p, there is a space charge region, there is a depletion region. This region we are calling avalanche region. Why? Because with increasing doping atoms or highly doping atoms, here electric field is increasing. Okay, electric field is increasing, and also carrier concentration also increasing in this region. So if you give high reverse bias voltage to this junctions, okay, we are providing high reverse bias voltage. Okay, after that, in this reverse bias voltage, whatever electrons are there, generated electron holes by light. Okay, by light we are generating electron holes. These electron holes are separating, but from the reverse bias voltage, these electrons getting sufficient high kinetic energy. So once this kinetic energy is getting, this electron make collision with neutral atoms or ionized atoms. Okay, that is plus charge, this is zero charge. Okay, once this electron make collision with the donor atoms or ionized donor atoms, they will generate one more extra electron. They will generate one more extra electron. So this process will continue. Okay, that's why we are even one photon we are creating two electrons. Okay, and 6 photons, suppose we are creating 12 electrons. Suppose 20 photon we are creating 40 electrons. So this is what multiplication process. Okay, this is what multiplication process. Okay, now we will understand in the form of diagram, band diagram. Okay, is it clear to you what is the principle of avalanche photodiode? Anyone? You got the clear answer? What is the avalanche photodiode? Please respond. Anyone? So okay, I will explain this one. After that, I will ask. Okay. So first we will take a p n plus region, in a reverse bias condition. Suppose if you take p type semiconductor here, okay, the Fermi level is close to the conduction valence band. Okay, and we are taking n type semiconductor. Okay, here n type semiconductor we are taking. So generally n type semiconductor Fermi level is close to the conduction band. Okay, conduction band. But our case we are taking n plus region. Why? That means highly doped semiconductor. That means Fermi level. What happened to Fermi level? Suppose if you draw n-type semiconductor and n plus is the highly doped. So what is the difference between these two semiconductors? How the Fermi level will change in these two semiconductors? If doping is
Sir,
increased, what? Yes, please.
your voice is coming fast. Network issue also.
Just checking. Just a second. Now is it okay?
Yeah, sir. Now
Hello.
okay.
Okay. So we know in n semiconductor the Fermi level is suppose here. Okay. Now if you take n plus region, the Fermi level is goes up, right? Why? Because even n plus region is adding more number of free electrons. That means we are creating more number of
Start
free electrons. Sorry.
again. Again, it's coming fast forward, sir.
Fast
Yes,
forward.
sir.
Yeah, actually, one thing here I want to say. Actually, this tab little bit response is low. That's why voice is this writing is coming little late, isn't it? That is the
Right.
thing.
And your explanation is very fast, sir.
The
Oh,
voice is going in fast speed, sir.
okay. Just I will write and then I will explain. Just a second. This is sometime. Okay, anyway. Hmm. See here. Okay. So I'm drawing here. Just, this is here. So can you see this band diagram? Only energy levels I have drawn left side and right side.
Yes, sir.
So here see dotted line is in case of n type semiconductor. Doping is moderate. Okay. Here the solid line is okay. Solid Fermi level is due to highly doped region. Why? Because the Fermi level is shifted upside. Fermi level is shifted upside because if doping is increasing means we are increasing the number of free electrons in a semiconductor. That's why if you compare to n-type semiconductor, n plus semiconductor, the Fermi level is more close to the conduction band. Okay, that is why I am drawing here the conduction Fermi level is very Fermi very close to the conduction band. Okay, that is what we have drawn here. Okay, so the Fermi level is n plus means Fermi level is more closer to the conduction band. Okay. Now we have drawn separate these levels. Now our job is to add this conduction band of p type semiconductor to conduction band of n plus semiconductor. Okay. Now I am joining these two. Okay. Just I have drawn valence bands. Now we have drawn this band bending. So here we are applying reverse bias voltage. Reverse bias voltage means negative terminal is connected to always p type p plus p semiconductor and n plus semiconductor is connected to positive terminal. Okay, because of this we know depletion region also increases, right? Depletion region increases in this junction. Okay, right. Now we have drawn PN junction semiconductor, PN junction diode, and we applied reverse bias condition. And you consider here we are applying high reverse bias voltage. Here we are applying very high reverse bias voltage. If you increase high reverse bias voltage, the band bending will increase. Band bending will increase and depletion width also increase. Okay. So here I am for your convenient I am drawing here at the interface here minus charges and here positive charges in the depletion region I am drawing. Okay, this is what we have discussed earlier also. In the p side we'll get the negative acceptor density and n side will get positive acceptor density. That is when you form the pn junction. Okay, now we are shining light here. Okay, we are shining light throughout the semiconductor. Okay, we are shining the light throughout the semiconductor. So In bulk region also electron holes will be generated, but this will be recombined. There is no use. Okay. So whatever electron holes generated in the depletion region are very useful because here internal electric field is present. Okay. This electric field is always, direction is positive to negative. Okay. In this electric field, because of this electric field, whatever generated electron holes will move opposite direction. Suppose here holes are generated, this will move towards the p region. Okay. And this electron move towards the n region. Okay. While moving this n region, so here we have applied high reverse bias voltage, very high reverse bias voltage, and also high depletion with high doping is there. So because it's high reverse bias voltage, these electrons, whatever electrons generated in the depletion region or space charge region, getting high kinetic energy or high energy they are receiving from the reverse bias voltage. While going to the towards n side, the electrons here interact with positive ionized donor atoms. Okay. So again in this depletion region, once electron interact this positive donor atom, it will create one more electron. One more electron. This electron we are calling secondary electron. Okay. This process we are calling impact ionization. What is that? Impact ionization. Here simple thing, very simple. We are using high reverse bias voltage. Okay. This energy, electron taking this energy, and this electron making collision with donor atoms, ionized donor atoms, and producing one more electron. Along with this electron, there is a one more electron. So here we are creating two electrons with one photon. With one photon, we are creating two electrons. This is simple example. Suppose if you use 100 photons, you can create 200 electrons. So light is very less. We are creating less electron holes, but we are utilizing this impact ionization and reverse bias voltage. We are creating extra electrons in the depletion region. Okay, so that if electrons are increased, this means the photo current also increasing. The photo current also increasing. This is what here, if you take current in this generated current is, suppose IP is M into, so here IN. Okay, IN. This is M is the IP is equal to M into IN. This M is multiplication factor. Okay, multiplication factor. Okay, you can write it down here. Multiplication. Okay, factor. Okay, that is why even light is low, we are producing high current. Okay, that is the advantage of this avalanche photodiode. Okay, is it clear to you how the avalanche photodiode is working? Anybody please respond.
Yes, sir.
Only very same concept. First we know PN junction diode, and we applied this is reverse bias voltage. Okay, so here in reverse bias we are applying high voltage, high reverse bias voltage. That is first point. After that, second thing, using light we are generating electron holes. Okay, we know in the depletion region, because of this internal electric field, the electrons holes are separating. So, and also using this high reverse bias voltage, these electrons getting high energy and they are making collision with donor atoms or ionized donor atoms. So once they hit that one, so suppose here I am drawing one more diagram here. See here. Suppose here nucleus is there. Okay, nucleus and orbitals are there. We know orbitals. So in these orbitals, okay, here electrons revolve around the nucleus. That you know clearly. So this is the just nucleus and electrons revolve around the this thing. When you incident some light, suppose we have studied Compton effect or any other. Okay, suppose X-rays. X-rays means also it is a fast moving electrons, high energy, fast moving electrons. So these electrons we are hitting. So these X-rays or electrons eject this one more electron. This electron will original electron is there. Along that, that will hit one more electron, that will eject one more electron from the nucleus. So here in this collision, we are using one electron, we are generating two electrons. That is what a collision, in collision this process happening. Same thing here also happening. Electrons getting sufficient kinetic energy, sufficient energy from reverse bias voltage. So after getting energy, whatever generated electron, holes will go towards p side and electrons go towards n side. While going on this way of electrons, the electron make collision with donor atoms or ionized donor atoms. Okay. In this collision, the electrons eject one more electron. These electron we are calling secondary electron. This collision process we are calling impact ionization. Ionization is nothing but, just suppose here phosphorus atom is there. Okay. Ionization means once you this leave the electron, okay, it will get positive charge, and once you this leave the electron. That is what ionization means. Ionization means whether it may lose hole or it may lose electron. Okay, once that leave electron, it will get positive charge, or once it will receive electron, it will get negative charge. This is what we are calling ionization. Okay, instead of neutral means equal number of electron protons, but here either electron receive or leave. That is what we are calling ionization. Impact means the electron is making collision with this positive donor atoms or neutral donor atoms. So it is creating one more extra electron. So here electric field also high in the depletion region, internal electric field. These whatever after collision, two electrons are generating, right? Two electrons are generating. These electrons also swept out towards the end region because internal electric field is very high in the depletion region. Because of this high electric field, electrons immediately swept out from this depletion region, and also holes will swept out towards the p region. In this way, we are immediately separating photo generated electrons and impact ionization in the electron generated in the impact ionization also, and photo generated electrons also we are separating using internal electric field. And at a time we are getting high current, even light intensity is low, but we are getting high current. That is the main advantage and working of these photodiode. Okay, the advanced applications are, you can use detector and voltage rectifiers and circuit diagrams. The advantage is light is low. Okay, light is low also, this will perform good. Okay, performance is very good. That is the main advantage. Okay, is it clear to you how the photodiode is working now? Is it clear, guys? How the avalanche
Yes.
photodiode is same thing, only just here we are using impact ionization. So we are giving high energy. Okay, we are giving high energy to electron. Okay, this electron making collision with phosphorus atom, this donor atoms. Okay, this is uh, making collision with donor atoms or ionized donor atoms. We are drawing plus sign. Okay, and also it is creating one more extra electron. One is original electron, this is secondary electron, one is original electron. Okay, that is why here light intensity is low, but still we are producing high current. That is the advantages. Only we are using this collision, this impact ionization process. So here one electron, we are creating two electrons. Suppose if two electrons are there, we are creating four electrons. If six electrons are there, we are creating 12 electrons. So this is what we are calling a multiplication process, multiplying 2 to 2 to like that. Every electron is generating two electrons. It is a multiplication process. That's why when you write current equation, IP is equal to M into I N, we have written. This I is the simple current, photodiode current, but M factor is multiplication factor in a device. Okay. Now we will see circuit diagram. That is also easy, same thing only. Just here we'll see how we'll draw the circuit diagram. So here we'll draw again this one. Okay, and just drawing little bigger diagram. Here P plus region. Okay, and this is I region. Okay, this is I region, and here we have P and N plus region. Okay, this P and N plus region is the avalanche region. Okay, avalanche region. Here we have done P plus region, and in the middle I region, and after that P again, after that N plus region. Okay, this P and N plus region is the avalanche region. Here multiplication process happens. Okay, in this region. Okay, here first thing we have to apply reverse bias voltage. That we will do it here. Okay, reverse bias voltage. So here two potential symbols I have drawn because very high reverse bias voltage. That is mean. Okay, that means high reverse bias voltage. Okay. So after that, here you can write here also as usual. Last time we have connected same thing. Here also we are connecting one resistor to protect our current, and here you are apply voltage drop. Okay. So here you can connect one ammeter also to measure how much current is flowing. Okay. Here through P layer we are shining the light. Okay. In case of sorry, mute. We are sending the photons from p-type semiconductor. We are sending the photons through p-type semiconductor, and here every region, every layer electron holes will be generated. Okay, but in the deeply in the bulk regions electron hole recombine, but only in the space charge region. Okay, in the space charge region only electron holes will be separated by internal electric field. That is only useful for the producing the current in a diode. Okay, like that here also every junction there is a depletion region. Okay, that is you can draw it or without drawing also, no problem. This is a simple circuit diagram. Okay, is this P and N plus region is the avalanche region, multiplication region. In this region only we are multiplying the generated electrons in this region. Okay, that is the main advantage of this region. That's why we are doing N plus is very highly doped. Okay, so this is the simple thing. So characteristics also you can simply draw this way. Okay, photodiode. This is a simple diagram. Okay. First one is dark. Okay, this is dark characteristic, and second one is photo. In case of photo, same thing. If you increase the intensity or reverse bias, also this current will shift towards the downside. Okay, or just wait, I will try it. Characteristics are high here. This is dark. Okay, first one is dark. Second, this is current and voltage. If you increase or if you apply reverse bias voltage and you shine the light, the curve will shift down. Okay. Second one is photo curve. This is same. IV characteristics and circuit diagram is same. Only thing is here we are using PIN structure and we are applying high reverse bias voltage. With this reverse bias voltage, whatever generated electron holes in the depletion region getting high energy from reverse bias voltage, and these electrons make collision with nearby donor atoms. In this collision extra electron is generating. So like that these generated electrons and photo generated electrons also immediately separate because of internal electric field. Okay, internal electric field is I immediately sweeps the out of the depletion region, and this will go to the contacts and we will collect these charge carriers. So here main advantage is light intensity is low, but using this impact ionization or multiplication process we are producing high current. That is the main thing, main application we are implemented in this photodiode. Okay, that is the thing. Okay, is it clear to you everyone how this is working condition of photodiode? Is it clear you guys? Any doubt here? Are you having any doubt?
So once again explain, sir.
Okay, see. Here, see, I will explain. Just I will take new page. Here I'm just drawing this normal diagram. Okay, normal diagram. This is reverse bias I'm applying. Okay, just this N plus region or N region. Okay, here we are applying reverse bias voltage, high reverse bias voltage. Okay, you remember that. So here interface we have, a negative P side negative acceptor density and N side positive acceptor density is there. This is simple PN junction diode we have discussed. Okay, PN junction and reverse bias. Okay, PN junction and reverse bias. And here, this is reverse bias, high reverse. If you increase reverse bias, high reverse bias voltage, the depletion width also increase. Here, because of plus and negative charge, there is a electric field, internal electric field. Okay, internal electric field is there. So high reverse bias voltage, high internal electric field is there. This reverse bias is higher, internal electric field also large. So this is the reverse bias. We connected reverse bias. Then now our job is to shine light. Okay. Here the light intensity is very less. Okay, light intensity is very less. And here also, once you shine the light, some of the electrons force will be created. Because of this internal electric field, okay, generated holes will go towards P side, right? And generated electrons will go towards N side. While going this towards N side, these electrons will make collision with positive donor atoms. Electron, this will make a collision. Okay, this will make a collision. And when electron interact with donor atoms, one more electron will be generated. One more electron will be generated. So here photo intensity is less. That's why we are creating less number of electron and holes. So this less number of electrons, we are applying high reverse bias voltage. Then these electrons getting high energy. Once these get high energy, they will interact with donor atoms, or they will make collision with these donor atoms. Once these interact, they will eject one more electron. These electron we are calling secondary electrons. Secondary electrons. So primary electron is there, that is incident electron, and ejected electron is secondary electron. So here using one electron, we are creating two electrons. We are generating two electrons. That is why using high reverse bias voltage, we are giving high energy to electrons at the depletion region, and these electrons gaining sufficient energy and making collision, and they are generating one more electron. That's why current intensity is low. We have one photon, but we have created one electron, one hole. In this one photon, but here we are using high reverse bias voltage, and using this electron, again we are creating two electron. So that means finally we are using one photon, we are creating two electrons. We are creating two electrons. That is what multiplication process. Okay, that is what multiplication process. So you may have doubt how the electrons are generating other electron. So here we have drawing a nucleus. In this nucleus, electrons revolve around the nucleus. You know that thing. So suppose if you incident some high energy X-rays, suppose you say X-rays, when electrons X-rays hit these electrons or nucleus, this will eject one electron and X-rays will go other direction. So X-rays will go another direction and electron also recoil in different direction. So here X-rays means high energy electrons. X-rays means high energy electrons. Using one electron, we are creating two electrons. So one electron we are using, and we are ejecting one more extra electron. That is what this X-ray collision means. Same thing happen here also. Electrons getting high energy from reverse bias voltage. These electrons making collision with another positive donor or neutral donor atoms. Okay. In this collision or in this process, this electron ejecting one more electron, because electron having sufficient energy to eject that electron. Okay. Once this electron having sufficient energy only, this can eject. Otherwise, this will not eject. Okay, that is the thing. So electron having sufficient energy and ejecting one electron from donor atoms or neutral donor or ionized donor atom. So this way electrons are generating one electron generating another electron, and these generated electrons also immediately sweeping out of the space charge region because there is a high internal electric field also present. Because of this one, huge current is producing in a circuit. Avalanche means rapid increase in current or electrons or holes, whatever you can say. Avalanche means rapid increase. Okay, very highly increment. Okay, that is the thing. So the main concept of this photodiode is light intensity is low, so we can create less number of electron holes. So if less number of electron holes are there, our response is very less. So to rectify this problem, we are applying high reverse bias voltage. If you apply high reverse bias voltage, the generated electrons by photons are light, getting some energy from this reverse bias voltage. This energy is more than sufficient to eject one more electron from the donor atoms. The generated electrons having sufficient energy from reverse bias voltage and they are ejecting one more electron. So even light intensity is low, current is high because this impact ionization or multiplication process. Okay, that is the advantage of this avalanche photodiode. Okay, is this clear to you? Is this clear to you guys? Avalanche photodiode.
Yes, sir.
Okay, please go through once this text, whatever this concept. I will send you notes also. Anyway, you have books. Once you read, it will be definitely clear this concept. Otherwise, you can ask me also if you while go through once you go through once and ask me question, then I will clear. I will explain again. No problem. Okay. So we have time also, sufficient time also. First two you go through one time. Then, if you have doubts, please ask me. Okay. Then I'm present. I am stopping class tomorrow.